had put the minus with the y instead of the z, then it would open, you know, just take this apple core and do it this way. If it's minus plus plus, then it's like this. Anyhow, what if we change two signs? What if we make it x squared over a? Let's put that one a minus, and the next one a minus. If there are two signs, what do we get? I think I heard that. Anyhow, for this one, now there is no xy trace. If it's equal to 0, again, I got negative equals positive. But I can have some
square on the 8.
What now?
Square on the 8.
Square on the 8, thank you. So basically, the xy plane breaks it up into two parts. And what we have here, the yz trace is a hyperbola opening along z. And the xz trace is a hyperbola opening along z. And so basically we've got this kind of little deal going on here. Okay? And it's still called a hyperboloid, but we have to make some distinction. Since we have two parts here and only one part over there, this is called a hyperboloid of one sheet, and this is called a hyperboloid of two sheets. And that word I said is sheet, like bed sheets. All right. And here, if I put B equal to C, that doesn't really give me anything special. But if I put A equal to B, that gives me a circular hyperboloid of one sheet. And again, if the two signs that are the same, if you put those coefficients the same also, then you'll get a circular whatever. So this would be if A and B are equal, this would be a circular hyperboloid of two sheets. Now, what do hyperbolas, we're back in two dimensions, what do hyperbolas have that parabolas and circles and ellipses do not have? Asymptotes. Okay, so let's talk about the asymptotes of a hyperbola. And then we're going to do the asymptotes of a hyperboloid. So anyway, if I had here an A minus A, then the directions for the asymptotes, well, they're supposed to be the same in all directions, but I botched that one. And here I made it curve away from the asymptote. That's no good. But anyway, so if I were to run up here to that thing and then go across to there, and I've made a little rectangle out of it, and I cheated on this southeast corner here. But anyway, this would be the B. And if I were to double the A and the B, I could do another hyperbola. It would have the same asymptotes if I doubled the A and the B. And if I did that, I'd have x squared over 4a squared, because that's really 2a, quantity squared, and minus y squared over 4b squared equals 1. Well, if I multiply that by 4, I just have a different constant on the other side instead of 1. And so what I'm saying is, basically, if I want to make this go out, I'll just get something bigger than 1. But if I want to pull it in, I'll make this thing go less than 1. And if I pull it in all the way, this number will become 0. Well, suppose I make it 0, x squared over a squared minus y squared over b squared equals 0. Oh, so that's just x over a equals plus or minus the square root of y, square root of y squared over b squared, anyway, plus or minus y over b. And those are linear. That's the equations of the asymptotes. And if I then kept on going, so let's see, 4, 1, 0, suppose I went to -1. If I make this a -1, well, that would be like just multiply by -1, you'd have a minus on the x squared and plus on the y squared, which would mean it would open the other way. So we got 2 families of hyperbolas in the plane here, and they have the same asymptotes. Well, now let's play that game in 3 dimensions. So again, if I were to take this and make it like a 4 or a 10 or whatever, what it would do is it would broaden this whole thing out here. It would intersect the xy plane further out. But if I make it smaller, then it brings this in. And when I bring it into 0, what kind of figure do I have? Cone. So the asymptotes of a hyperboloid would be a cone. And I can put these inside the cone and have the same kind of thing going on. So that means that for a cone, I get x squared over a squared plus y squared over b squared. And I'm making this, let's see, equals c squared over c squared. So I'm just saying, once I've got this with 0, I might as well make it all positive by throwing that to the other side. And that's the one I'm really interested in. It's a cone, but I want to show you how all this works. So, still got paraboloids. I might do them some other time. And there are elliptical paraboloids and circular paraboloids and hyperbolic paraboloids. I mean, just the whole zoo out there of quadrant surfaces. But now that I've gotten here, I'm going to go with cones. And so this is a double cone. Well, double cone with the vertex at the origin. And what I want the vertex to be above the origin. So I'm going to take this cone and push it upwards. How do I do that with the algebra?
Z minus h squared.
I'm sorry, what?
Z minus h squared.
Z minus h what? Oh, you mean replace that? Okay, yeah. So if I do z minus h and then just plug that in, then that will push this up, and I'll have something like this. So that's what I want. And anyhow, first of all, I want it to be circular, because that's the kinds of cones we're most familiar with. So A equals B to make it circular. And while we're at it, let's see, I want A to be my radius, and I want H to be my height. So let's check that out. Let me go over here. Well, actually, I got my picture right there. So I've got this point up here is 0, 0, H. And then on the bottom here, I want this circle to be x squared plus y squared equals a squared. For z equals 0, I want this. Well, if I look at this equation, so again, as we saw earlier, if A and B are the same, I've got a common denominator, so I can do it this way. If I put z equals 0, then what I have is negative h squared, so it's positive h squared. And I'm dividing it by something. And over here, what I want is that circle. So I want x squared plus y squared equal a squared. This will be a squared over a squared. Well, that's just 1. So I want question mark to be h squared. And actually, I should have done it the other way. I should have looked at the top. If x and y are both 0, then I want this to be 0, so that'll be z equals h there. Well, I guess I need to look at both ends. Anyway, so my equation finally is x squared plus y squared over a squared equals z minus h squared over h squared. There it is. Now, I want to solve it for z. So first of all, I want z over here on the left. That's just my own hang-up. A lot of people have that hang-up. Oh, by the way, time in. I'm going to be working with the code now. So let's see. I have z minus h squared equals h squared, and I'm just going to move the a squared over here with the h squared, x squared plus y squared. All right? So then z minus h is plus or minus the square root of all this mess. And so z is going to be h plus or minus h over a times the square root of x squared plus y squared. Do I want the plus or the minus? What? The plus. And the reason I want the plus is because it's positive, right? Except, wait a minute. Where is h? H is up here.
We want the minus.
I want the minus.
I wanted to want the plus.
Oh yes, okay, because we always get the plus. But it's cool when sometimes we get a minus. So h plus the square root would have been the top part of this wigwam or whatever. But for the bottom part, it's h minus. So now we finally have our function. That's probably the most complicated working out of a function we're going to have this semester. I'm going to factor out the h while I'm at it. 1 minus 1 over a times the square root. So that's my function. And I have this circular base. So I have to do an integral over the x squared plus y squared equals a squared of this silly function. we choose an order of integration, et cetera, et cetera, et cetera. And since we've already done an integral over a circle to do the cylinder, we already know what the limits will be. Now, let's suppose I do choose dy dx. So then I have to do my y interval first. What do I do? So this part, no problem. I would separate this into a double integral of h dy dx. And oh, that's my cylinder right there, right? So this is going to come out pi squared h. And then minus this other part. And again, I'm asking, what technique of integration would I use here? I'll just do a trig sum. So I've got a square root of a quadratic, and the method of last resort, the fallback method for square roots of quadratics is trig sum. So I'm going to substitute for y, and which trig function would it be? When I have a constant, so I'm holding x constant, so it's a constant plus a perfect square. The three possibilities are constant minus perfect square, constant plus perfect square, and perfect square minus a constant. And one of them is sine, one of them is tangent, one of them is secant. This one is tangent. Yeah, it's tangent because of this identity. That's what gets the job done. We want this thing to become a square root of a monomial so that we can just get rid of the square root. And this is the way it happens. So I'm going to get a secant squared, square root of secant, square root of secant, or minus secant sometimes. But anyway, so this would be a trig substitution. X, tangent, theta. And I gave you another example in which this is a good substitution. That's the last problem on supplement, whatever we're at now, 5. So I hope you worked that one also. Anyway, we try it here. We're going to get a secant, and then the differential gives a secant squared, so we're going to end up with a secant cubed integral. Now that's one of the more difficult integrals that you ever have to do. Secant cubed. Well, it's not as bad as secant to the fifth, but anyway. And what's the most prominent feature of the answer when you do the antiderivative of secant cubed?
The prominent.
Most prominent feature. Well, how about if we just say secant? The odd powers of secant are odd. I mean, they're peculiar. What happens when you do the integral of the secant? What's that? Because it only gets worse for secant cubed.
Secant tangent?
No, that would be the derivative. I want the antiderivative.
So 1 over cosine.
Well, that's 1 over cosine.
Oh wait, the integral for secant is natural log.
Natural log, that's all you need to say right there. But for the rest of it, secant is equal to. So I'm going to get logarithms in here. Does the answer for the cone involve logarithms?
No.
Pi squared h over 3. No, no logarithms. So this is a really grungy way to do this. And I went through and followed it out. I worked it all through. I said those logarithms have to disappear somewhere. It took me 9 pages. I remember that distinctly. It took me 9 pages to work that thing. And I've done it once or twice since then, and it still took me 9. Well, a lot of pages anyway. But there's, it's an orgy of L'Hopital rule and all that sort of thing, because the logarithms have to disappear somehow. Anyway, we're not going to work it this way. I deliberately went down this road because I think you need to see some of these things. And when you work on other, the quadratic surfaces are among the most common geometric shapes that you have to deal with in calculus. So anyway, I did want to go through all of this. But I would also like to get an answer tonight. So what I'm going to do is basically the same thing I did for the cylinder. I'm going to turn this thing sideways. And when I turn it sideways, it doesn't matter where the vertex is. We might as well put the vertex at the origin. So, and I'm going to use symmetry. So I'm going to take a fourth of a cone. This is a right angle here. That's not a right angle, even if it looks like a right angle. We're going to multiply this thing by 4. And so for this cone, tell me about the equation. The main axis of this cone is which axis? The Y axis. All right, so the main axis is the one that's different from the others. So I'm going to have x squared over a squared and y squared over b squared and z squared over c squared. And how do we make this one different from the others? Y is negative, okay. And I'm going to put A and C equal. And guess what B is going to turn out to be? Okay. So then I solve it for Z. Get rid of this ugly thing. So I've got Z squared over A squared equals Y squared over H squared minus x squared over a squared. I'm going to take the square root and I'm going to multiply by a. And it would be plus or minus, but this time it's plus, because it's above. The other one was above the line also, but that would turn out to be right, because it was below something else. All right, so there is my function. And I'm going to put the a inside, so this will be the square root of a squared, essentially. So I'm going to have a squared y squared over h squared minus just plain x squared. Okay? And what kind of base do I have here? Triangle. So when I did this with the cylinder, I had a rectangular base. That made it real easy. This one will be a little bit tougher, but it won't be more than 15 minutes tough. So anyhow, the volume of the cone will be 4 times the integral of this function over some triangle. Well, it's a right triangle, actually. And I'm going to choose an order of integration. And my choices here, of course, are my usual dy dx and dx dy. And I want to know which one to do. So if I set it up, and there'll be trig substitutions either way, right? If I do dy dx, then there's my variable, there's my constant. What's the trig sub that you need for a perfect square minus a constant? As opposed to this one where it's if I put y on the outside, then this will be constant minus perfect square. The perfect square minus constant? No. So again, the key over here was the identity that it fit into. if I do the sine, what's the identity that goes with that? Sine squared plus cosine squared is 1. And so then putting that across there, I've got 1 minus sine squared. And so if I'm going to do a sine, I need my trig function to be where the minus is. So that would be dx dy. This will be for sine. And then what about the other one? That would be the secant. So if I take this 1 and move it over here, then I'm doing the secant substitution. Well, guess what? If you get secants in there, you're doomed. All right? So we don't want this one. We don't want that one. When you do the substitution, when you do the square root, you're going to get a tangent. Secant squared minus 1 gives you tangent. And then the dy would be secant tangent times d theta. So that would be secant times tangent squared, which is just as bad, if not worse, than secant cubed. So anyway, here's what's really going on. Remember I said that the whole basis of this double integral thing for volume was the cross sections. We're integrating cross-sectional areas. And so if we've got the cone in the upright position, and I do cross sections, what do I get? What? That's what you'd think. And you do get a triangle if you do the plane of the board. But if you were getting triangles, then what you would have is a ridge along this cone. That would be like a pyramid, and you're dicing it on the bias. But anyway, it's not, it's curved. And remember, it's a double cone. So if I cut this in front of the board, I get a hyperbola. And when you do areas of hyperbolas, you get logarithms. And I'm having my Cal3 class look at a figure like this. It's on their latest supplement, and they're going to be getting logarithms after they go through some secant stuff. But anyway, the easiest way to see that you get logarithms is to turn that hyperbola the other way. Now, if I want to do area in here, I'm going to get the integral of 1 over x is logarithm. So anyway, we don't want that. And over here, if I slice it this way, I'm getting hyperbolas. But if I slice it the other way, I'm getting not triangles, circles, or quarter circles. Yes. All right. And so slicing it this way, I'm going in the y direction on the inside. That means I'm doing dy dx. So this dx dy, I'm hitting it this way. So let's go ahead and get it done. Get her done, as you guys said. All right. So I need some limits. Let me redraw the base. And here I really do need to draw the base, so I'm going to swing this down and turn it around. So the thumb is along the x-axis, and that's not where the triangle is. The triangle is up here. This is y equals h, and this is a. And so, let's see, I'm doing dx dy, so my limit's on y. Say 0 to h, thank you. All right, now I look at a typical y coordinate, about right here. Go in the direction of increasing x. So it goes in where? And comes out. Comes out, let's see, what is that line there? It's this line. It comes from the equation of the cone. So, what we have here is, let's see, it was all of this. So if I put z equal to 0, I've got x squared over a squared equals y squared over h squared. So solving it for y, no, we're solving it for x, aren't we? We need the x limits. So x is going to equal ay over h. Plus or minus? No, the minus is over here. So we get x equals ay over h. Or think about it another way. It's a straight line, for goodness sakes. What's the slope? So m here, let's see, this point is ah. So that's just h over a. So I get y equals h over a times x. Now solve it for x. So anyway, ay over h. Now, we're not going to contemplate that very long. We've got to do our tree stuff. X equals what? So it's going to be sine, but what's the coefficient? What? So when I'm doing the square root of a squared minus x squared, then it would be a times the sine, right? Well, this would be ay over h times the sine. So differential ay over h, and again, the y is being held constant. So I get ay over h cosine theta d theta. And I also worry about the square root. The square root will be a squared y squared over h squared minus a squared y squared over h squared sine squared theta. So I'm going to factor it out. I'll have ay over h times the square root of 1 minus sine squared. So this thing comes out 4 times the integral of ay over h cosine theta times ay over h cosine theta d theta. The 0 and h stay the same, right? But these limits are going to change. Well, one of them will anyway. That's still going to be 0. That'll still be 0 because the sine of 0 is 0. So if x is this 0, if x is 0, then sine theta is 0 and theta is 0. Now, what if x equals